So our dialogues continue with eminent colleagues, and the chairperson is changing with Professor Aris Rosakis from the Academy of Athens and the founding member of the Keynote of Academies. Sir.
It's my great pleasure to introduce two of our keynote speakers today. We're going, first of all, before I start, I just wanted to welcome everyone to the Academy of Athens and to the Keynote of all academies. This is a very important day for all of us here because it signals the Academy's wish to engage the world in a more systematic way. Our first speaker today is Professor Subra Suresh, who is a globally renowned engineer, scientist, and academic leader, whose career spans research, education, and public service at the highest level. He is the Vannevar Bush Professor Emeritus at MIT and Professor at Large at Brown University. And over the last 2 decades, he has led major institutions worldwide, serving as Dean of Engineering at MIT, as Director of the US National Science Foundation, as President of Carnegie Mellon University, and President of the Nanyang Technological Institution in Singapore. He's elected to all 3 US National Academies of Sciences, Engineering, and Medicine. He's a member of many other academies around the world. He is a recipient of the US National Medal of Science, the French Legion of Honor, and India's Padma Shri. And his work brings engineering, material science, biology, and global higher education together, making him one of the most influential scientific leaders of our time. Professor Suresh.
Thank you very much, Professor Rosakis. Good morning, everyone. It's a great pleasure and honor to be here today. I would like to start off my presentation with a topic that's been touched on in the introductory comments. We talk a lot about artificial intelligence. What I would like to focus on in the next 30 minutes or so is to look at deep learning from nature and also combining it with intrinsic or innate human intelligence and how we can benefit in science through what I call co-intelligence. So let me start with some examples. This is one of the plants that's familiar to many of us, Venus flytrap. It's unique in that it's a plant, but it's also a carnivore. It eats insects, and it behaves through stimuli that come from mechanical forces, chemical agents, and electrical stimuli. So you can see here in this picture that it has hair-like features. So when an object gets inside the Venus flytrap, if 2 hairs are triggered in some period of time, it closes shut. And then it waits. So what happens if it's just a dust particle and not an insect? It knows that it waits for some time. If there is no movement, it opens and releases it. If 3 hairs are triggered, then it knows that it probably is a meal for it. When 5 hairs are triggered, it completely closes shut, releases a chemical, kills the insect. And it knows which insect to kill. There is no point in wasting all this energy on tiny ants, so it knows which ones to choose. So and it can count to 5, because when 5 hairs are triggered, that's when it goes into full operation. So it knows some mathematics as well. So it's pretty remarkable. So why does it do this? If you talk to engineers, of course, this is all engineering. If you talk to chemists, it's all chemistry. If you talk to biologists, it's all biology. But there were some interesting experiments done to simulate this. So we know there is chemistry involved. We know there is mechanics involved because it opens and closes. There was a beautiful experiment done a few years ago when they thought, is there any electrical signal involved? So in this experiment, they did the following beautiful hypothesis. So when we go for surgery as humans, when we are anesthetized, we fall unconscious, we feel no pain, our electrical system shuts down, and then when the anesthesia wears off, we reawaken. So they used a similar process they used diethyl ether as a form of anesthetic, a vapor, anesthetized the venous flytrap, and it completely lost its ability to shut. When the anesthesia wore off, it opened up again. It is fully reversible, just like humans. So there is electrical signal involved in here. And it's not just chemistry, mechanics, and electricity, the electrical signals that are involved. Light, optics, and touch also play. So here is an example of Mimosa pudica, a plant also known as touch me not or shame plant. When you touch it, it'll curl up. And the speed with which it curls up is among the fastest in the plant world. And it's also very sensitive to light. There is another plant found in the South American Peruvian Andes called Nasa poisoniana. And this plant is remarkable in the sense that when pollinators come and feed the flower, it knows exactly which pollinators came at which frequency, and then it knows how to adjust its geometry so that it can respond to that particular pollinator, depending on the frequency of that particular pollinator. It's quite remarkable. So there are a lot of things about plants that are unique. So there was a discussion about intelligence and consciousness. The former president of Greece talked about consciousness. And do plants have consciousness? This is one of the raging debates in one of the books that came out last year. Vernalization refers to the ability of a plant to flower through prolonged cold winter. So things like tulips, garlic cloves, etc., have this ability. Circadian rhythms. So there is a plant, Cornish mallow, for example, it follows the sun. And when you try to do experiment where you try to confuse the plant by turning it in the wrong direction, it knows exactly how to turn in the direction of the sun, no matter how you try to disorient it intentionally. Then we have the question of intelligence. So if, for example, intelligence is defined as a quality where we use information from the past to make decisions about the future, many plants conform to that definition of intelligence. So when we talk about artificial intelligence, do plants have intelligence? So if this is the definition of intelligence, there are many examples in the plant kingdom that do this. So with this, we have the opportunity to learn from nature. Now we have the opportunity to learn from machines through machine learning. And of course, we have innate human intelligence. We know that machines can hallucinate. We do know that humans hallucinate. But most likely, nature doesn't hallucinate because nature's laws of thermodynamics, the universal truths of nature in physics, etc., cannot be violated. So if we combine all of this, what are some of the possibilities? Now, with the advances in computing hardware and software, we have come very far in scientific discoveries. We've also used not only just computational science and engineering, we've also used what is known as biomimetics, mimicking nature mimicking biology, mimicking plants and animals to create engineering devices. This has been around for some time. But what is new now in the last 5 years is the speed with which we can connect hitherto disparate disciplines is unprecedented because of things like large language models, because of AI. We can put 1,000 books together and have the machine read it in ways in which humans cannot possibly do. So if we can do that, and do that in a controlled way and the correct way, and on the positive side, can we extract information that cannot be extracted without the use of artificial intelligence? It's an interesting question. In other words, are there examples where we can do science in new ways today with all the tools that are available to us today with AI that is not possible without AI? So that's a question I want to answer with a couple of examples. So if we combine nature intelligence with machine intelligence and human intelligence, there is an opportunity for new discoveries, new scientific discoveries, new knowledge, and we want to make sure there are no hallucinations in this process, either from machines or from scientists. So to avoid this, our goal is to ensure that if the machine tells us something, we don't believe it. The only way we will believe it is whatever the machine tells us, we are able to go to the lab and reproduce it in a real experiment, so we can see it with our own eyes. Then we ensure that is one way to avoid hallucination with respect to new scientific discoveries. So I would like to walk you through a few of these in the next few minutes. So there are 3 areas in which we've been working over the last 7, 8 years. So all of this work is in the last 6 or 7 years. I'm going to start with plant science. To go into some very significant detail, I will focus significant time on this. Then I would like to go into material science, which is my field, and talk about an example, again from nature, and then finish with just a very simple example without going into any detail, one biomedical application. So one of the plants we started with, there are many plants that show this trait. The plant Pelargonium, its awn, which you see, when it's in the wet state, when it rains, the awn opens up, as you see in the picture to the left. When it's dry in sunlight, it curls up. So depending on moisture, it can open up or close. Then we thought, if plants can do this, how do we do this in engineering? In other words, let humidity be the driver. Can we create self-propelling robots that respond only to humidity? Can we create devices and objects that autonomously change shape when you change humidity? Can we make any shape we want just by changing humidity? If plants can do it, how do we learn from them? So I was very fortunate to collaborate this was a time when I was president of NTU in Singapore, collaborate with one of my colleagues, senior colleagues, Professor Nam Jun Cho, who's a material chemist. So we decided in 2018 that we will take a material from a plant. So this is a sunflower, and I did not know this at that time. The pollen from sunflower, when we think of pollen, we think of spring, and we think of sneezing and allergies. But sunflower, there are pollen from many flowers, but sunflower pollen, apparently, you can buy it on Amazon.com. You can buy kilograms after kilograms of pollen for a few dollars. So you see in the jar, this is sunflower pollen, and pollen is considered the diamond of the plant kingdom because it's extremely hard. So in the picture that you see a sunflower on your top left. In the middle is the grain, the pollen grain, which has very sharp spikes. If you look at it in the electron microscope, it has a very hard outer layer called extine and an inner layer called intine. So we had some challenges to do. We don't want to sneeze in the lab, so we want to make an allergenic pollen into a non-allergenic material, so we get rid of whatever causes the allergy. So how do we do this? We were very fortunate to work with some chemists. Apparently, using a process very similar to soap making, you can take the grain of pollen, go through a process where you use potassium hydroxide at some temperature and time, and then you play with it, just like chemists do. You can make the pollen non-allergenic, and you can take the hard pollen grain and convert it into a soft microgel. Once you have the soft microgel, just like metallurgists have done for millennia, the microgel becomes the building block of new materials. So you put them together, you assemble them, and you create any object that you want. So we were able to create the microgel. Then we thought, okay, what object do we create? We decided we're going to make paper out of it. Rather than paper from cutting down trees and out of wood, we're going to make paper out of pollen, an A4 size paper, or 8.5 by 11 in the US, and you can feed it into a printer, an inkjet printer or a laser printer, and see what comes out of it. So what you see in this figure is a paper being made, and then we can print on that paper just like you print on a wood paper. You can make a box out of it, you can make a coffee mug out of it, you can make anything you want. We decided to make paper out of it. But here comes the interesting part. It turns out that the pollen paper can absorb moisture, it can absorb humidity. So here is something we learned from semiconductor physics, from the way TSMC and Intel and Samsung work. So when you want to make computer chips, you take a large silicon wafer, which is perfectly flat, and you take the silicon wafer, and if you want to make a computer chip and you want conducting lines in the silicon chip, you say deposit copper on top of it. So let's take an example. I have a very flat silicon wafer. On top of it, I deposit copper film, a very thin copper film of a micrometer at slightly high temperature, above room temperature. Now think about what happens. As I cool it down from a slightly high temperature down to room temperature, the copper contracts as you cool it down, but silicon contracts differently. So you have two materials which contract differentially, and therefore an initially flat silicon wafer with a copper film on it, as you cool it down to room temperature, will no longer be flat because silicon contracts less compared to copper, so the substrate will be curved. When you measure the curvature is an indication of stress. So essentially, the silicon wafer curls, and this is one of the headaches in the microelectronics industry, how to avoid this so that your computer chips don't crash, your computer doesn't crash. So it's an interesting issue. So we adopt the same thing here for pollen. So what you see here is you have a thin strip on the left, figure A, is a pollen paper. We feed that paper into an inkjet printer, and we print lines on it. Just to keep the experiment extremely simple and clean, we keep the thickness of the line the same in all the experiments. We keep the spacing of the line the same. All we change is the orientation of the line with respect to the length of the paper. And you see the angle theta. By the way, that's the only Greek you will see in my presentation this morning. So the angle theta, we vary from 0 to 90. So we choose 4 angles, 0, 30, 60, and 90. Everything else is the same. So it's a very clean experiment. Now what we do, so we have a bilayer. If I now change the humidity, this is what we hypothesize. Physics tells us that the paper will absorb moisture as you go to high humidity, but the ink on the paper, the line, will not absorb moisture. So that means the paper will swell, but the line will not. So you have two materials, just like silicon and copper, and therefore an initially flat paper will start to curl. Our hypothesis is that if you change the angle, the paper will curl differently. Now we are in business. So now we can change shape by changing humidity. So here are 4 examples, 0, 30, 60, and 90 degrees. Now let's see if that works. So I'm going to start with this first movie. So we have the strip of paper. I'm going to start with an angle of 30 degrees. I start with low humidity, then I'm going to expose it to high humidity in a container. So as I start this, So the paper curls as I just change the humidity. Now if I go to 60 degrees instead, you'll see what happens. Now if I go to 90 degrees, so just by changing the angle, everything else being the same, I can create any shape I want. So it's an autonomous shape forming material. So then the national flower of Singapore is an orchid. So we decided to create an orchid. You can design it in your computer. It just takes a couple of very smart students. It took them half a day to design. And one of the remarkable things about this, so if you see the top row, you can print differently to make different curls, and you can put them together to make an orchid out of it. And you can design all of this digitally. So now, one of the remarkable things about plants is plants, so if you want to make a sharp corner, if you want to make a table, we make two surfaces, we connect them, we nail them, we weld them, we join them, we tape them, however we join. Plants don't do that. They have a different cell, and the cells adopt near the corner. So if that is the case, how do you create a box? How do you fold it so that you can create a sharp corner? So we print differently. So we learn from plants. So what you see here is we take a pollen paper, where the corners are supposed to be, we print ink on it, and then we change the humidity. So I'm going to show this movie. If I want to create a box, so I put a very heavy steel object in the middle, and we cut the corners with a pair of scissors to where it needs to fold, and then you can see the black lines. That's where we print the lines where the corners are supposed to be. So we start with low relative humidity, and when you change the humidity, it starts to fold exactly where you print the corners, just like plants do. This we wouldn't have known without observing plants. So nature intelligence comes in very handy. If you go back to the low humidity, if you switch from high to low humidity, you can see that it opens up. So you can coat it so that once you print something on it, it no longer is receptive to humidity, receptive to moisture. So the shape doesn't change anymore, and you can use biocompatible coatings. So to prove that, we printed, because it's sunflower pollen, we printed Van Gogh's sunflowers on the paper, and then we dip it in water to see what happens. And nothing will happen. It preserves the image that you print on the paper. Now, we are very worried about cybersecurity. The way we avoid cybersecurity we ensure cybersecurity on something printed is to shred the paper. We waste paper. We cut the trees, we waste paper. Can we print and unprint and reprint? Plants are very good at it. Plants are very good at adapting. Can we unprint? So we came up with a process where you print Van Gogh's sunflowers, you do a simple process, and you take everything out of but the paper is still intact. You go back to its original shape. So then you can go reprint again and keep doing it over and over again. So you preserve the paper. It's eco-friendly. So here we start at 12 o'clock with a clean sheet of pollen paper. We print Van Gogh's sunflowers on it. Then we unprint it. Then we get up at 6 o'clock, we get clean sheet of paper again. Now we print Mona Lisa, and then we unprint Mona Lisa, and then we go back. We did this 9 times in this cycle. The paper is still mechanically intact. We can preserve the paper. So this is another thing we learned from nature. So finally, we can do a lot of other things. For example, the pollen paper absorbs not just moisture, it can also absorb oil. If there is an oil spill, you can make a sponge, and you can suck in the oil to remove oil spills. In deep wound surgery, it's biocompatible, so you can put it in the body to absorb blood, to post-surgery and so forth. So there are many other applications. Here is an example. When we go for electrocardiogram to a cardiologist, they stick in all these plastic things on our body. There are 7 or 8 probes to measure the electrical pulses. electrical signals. And because there is glue, it's very painful. So instead of a plastic that you throw away, you can use pollen substrate. So we had a volunteer who had the regular EKG and EKG with a pollen substrate. You cannot tell the difference between the two signals in the human body. So these are examples of things that we learn from nature in this case. Now, this is only nature intelligence. Now, what do we do with machine intelligence on top of it? So we started a project at MIT with one of my colleagues, Professor Marcus Buehler. And the idea is the following. We feed literature that's been peer-reviewed into a large language model. And then we ask the program several questions. Tell me, how do I design this that I haven't thought of as a human? So the computer gives us examples. So here are two examples of questions. We know what coating to put to make the paper no longer susceptible to moisture. So that if I make a box, I can coat it, and then I can ship the box so that when it goes from, say, Greece to Arctic Circle or something like this, it doesn't change shape because there is difference in moisture. So you can do the coating. So we asked the program, what coating would you use, which is not in the literature. It suggested paraffin. So we actually went and did the experiment on paraffin, and we found that the program was actually right, even though we didn't think of it. We also asked it, what other shape would you create other than printing lines? So it came up with examples of leaves that plants use, and we were able to create different shapes. But the program also hallucinates. We asked it to give us a corrugated shape. It said print on both sides, and it doesn't work. We know it doesn't work because we have tried it and it failed, and when you have a negative experiment, you don't publish it. Nobody will publish it. We know from bad experience something doesn't work, but the computer doesn't know. So it makes false predictions because it doesn't have the wealth of experience that we do. So that's the problem with the large language models today, at least in this particular case. Let me go to the second example very quickly. And the second example is the hardest material found in nature, which is diamond. The question is, we know that if you take diamond in the nanoscale, for example, if you make a needle out of diamond, and the size of the needle is 1/100th of the thickness of the human hair, it's a nanoscale. The human hair is about 80 micrometers in diameter. If you go to 18 nanometers, which is 1,000th of the thickness of the human hair, you cannot see it with the naked eye, you have to put it in the microscope. We know that nano will behave differently than micro and macro. So how will it behave? For example, because diamond is the hardest material found in nature, we know we cannot bend macroscopic diamond. We cannot even bend microscopic diamond, but can you bend nanoscopic diamond? Can you bend diamond when it's in the nanoscale? Because the surface to volume ratio is very high, there are very few defects. So we decided to try it. One of my former postdocs, who's a professor in Hong Kong, he created this diamond needles on a silicon substrate. So we put it into a microscope. And this is the experiment. So here is a diamond needle that's sticking up, and this is nanoscale. I come with a diamond tip inside the microscope. I try to bend it. I have no idea. My hypothesis, we may be able to bend it because it's nano, but we had no idea. So we videotaped the experiment. We tried to bend it. Then we told the student, don't break it. So unbend it, retract it, go next time, bend it a little bit more, retract it, keep doing it until eventually it breaks, but take a video. And we can do that repeatedly. So what I'm going to show you in the next video is, to our surprise, at room temperature, we could bend diamond. And what you see on the left is a real experiment. What you see on the right is a computer simulation. Because diamond is elastic, we can actually simulate it. And the color contours show the strain in the diamond as it bends, and the maximum strain is 9%, because in macro scale, diamond will fracture catastrophically at a strain of 0.1%. But in nanoscale, you can bend it to 9%, which was unexpected. So the question is, so what? We can bend diamond, what do you do with it? Diamond is also an electronic material. It's an ultra-wide bandgap material. and it has a band gap of 5.6 electron volts for physicists in the audience. Let me show you when you actually break diamond, how it breaks. This is how diamond will break if you let it break catastrophically. And the angle at which it breaks, you can actually predict it. So now we go to microelectronics and optoelectronics. Diamond is an electronic material with a band gap of 5.6, which is somewhere here. And silicon is here with a band gap of about 1.2. And the color contours show the colors of so-called compound semiconductors, which are used in electronics industry. So the holy grail question is this: can you take diamond, can you bend it? By bending it, can you change the band gap, its electronic properties, without changing the chemistry? In other words, can you change it mechanically and not through chemistry? To answer that, you have to do simulations in 6-dimensional space. The fastest computers today cannot do that easily. So what we do, our only way out is AI. So we do 1,000 calculations with molecular structures, atomic structures. We go to neural networks, and then we ask the computer to predict for us, the program to predict for us where the diamond band gap will change without changing the electronic structure and the atomic arrangement of diamond. You cannot have graphite, for example, then it's a useless experiment. So we were able to do that computationally, and we showed that you can not only bring the band gap of diamond, essentially make diamond behave like silicon just from an electrical conductivity point of view. You can also change the thermal properties of diamond significantly. And the lesson you learn here is there is an opportunity to change the properties significantly in unexpected ways, not by changing chemistry, but through mechanical means alone. And this is an example where today we cannot do it without AI. This scientific finding cannot come about without AI. It can only be done with AI. So that's the second example that I wanted to show. So here is pictures of the third picture in green that you see, the bent needle, that's band gap. And you can see the band gap going from 5.5, 5.6 to 0. The color of diamond also changes when you change the band gap. So, and then on the right, you see the thermal conductivity. So let me finish with the last 2 slides. There are many, many biomedical applications that many people are working on, and one of them that I want to highlight is diabetic retinopathy. With the increase in diabetes, microaneurysms in the blood vessels in the eye can be a significant problem, which in serious cases can lead to blindness. So by combining real experiments using microfluidics, so a thumbnail-like feature that you can create like a computer chip, inside that you put human blood from a diabetic patient, and then you get images from the patient's eye, from the doctor, and you can actually do experiments to measure the blood flow in the microfluidic device. That, combined with images from the patient, can be put through an AI algorithm that can help the clinician treat the patient better with more information. That's the goal. So here is an example of simulating microaneurysm in a lab device and putting the diabetic patient's blood into the device, and then extracting very precisely things like velocity, pressure, and stress in the device to do some calculations that cannot be done without AI. And this is what we refer to as artificial intelligence velocimetry. So with that, I would like to conclude with three, 4 observations. And this is an image of starlings doing a dance at night. Nature works in ways that we don't understand. Thousands of these birds at sunset gather, and remarkably, they do this dance together. And this is one of the things that we don't understand, why they exactly do this. So one of the things we have seen in the 3 examples that I've shown is nature intelligence can be very powerful to do engineering devices. And I just showed a few examples. There are many, many other examples that one can think about. That combined with machine intelligence provides potential possibilities if it's used in the right way to make scientific advances. This was referred to earlier, intelligence and consciousness in plants. It's an interesting topic, a very controversial topic, and this is something that people in the plant science community are working on. Potential pathways to new science and technologies through this collaborative intelligence or co-intelligence. And finally, multi-fidelity approaches by combining low fidelity and high fidelity data with real experiments. To avoid hallucination, we made the decision that if we cannot do this in the lab, we don't believe anything that comes out of the machine, including our own calculations. So we have to reproduce it in the lab. That's our hallucination proof. Thank you very much.
Thank you very much, Professor Suresh, for a wonderful presentation. It is now my great pleasure to introduce our next speaker, Professor Hans-Joachim Schellnhuber. He goes with the name of John. So John is a world-renowned German atmospheric physicist and a leading authority on climate science. As the founding director of the Potsdam Institute for Climate Impact Research, he has shaped modern climate policy for over 3 decades. He's perhaps best known for pioneering the 2-degree guardrail concept, now a global standard, and for his critical research on climate tipping points. A former advisor to Pope Francis, Angela Merkel, and the European Commission, John was a member of the IPCC team that was awarded the 2007 Nobel Prize in peace, and currently he focuses on regenerative architecture through his initiative Bauhaus Earth, advocating for buildings that act as carbon sinks. Before I introduce John, I want to say that John started as a theoretical physicist, and he's truly a Renaissance scientist, and it's a pleasure to welcome him.
Thanks so much for the introduction. Yeah, distinguished audience, it's a big honor to be here in the very hall where I was introduced a few years ago as a member of the Academy of Athens, the mother of all academies. And I would like to thank Christos Serifos for this amazing initiative. Let me make 2 preliminary remarks. So first of all, I did not orchestrate my talk with Professor Suresh. He talked a lot about natural intelligence, human intelligence, and how artificial intelligence can help us to make it an integrated understanding of our universe. But I will actually complement what he has told us in his absolutely fascinating talk. The second remark, just a spontaneous idea that crossed my mind while he talked, and particularly in the last slide, and the former president of Greece also referred to that, what is consciousness? And we have not solved this riddle yet. Maybe we will be able to do so. And do plants and animals, for example, have consciousness? It's a question we cannot really answer. And it reminds me of a little anecdote. So a long-term friend of mine, and this is not exaggerated, is the former Prince of Wales, now King Charles III of England. And he was always ridiculed and in the yellow press. And one day I said, and he told me about it, I said, John, I was ridiculed. People made fun of me because they said, "You are talking to plants." And he said, "John," and I really did, and I learned a lot from that. So, you see, natural intelligence. So my talk is high-tech meets no-tech, and I really mean no-tech. Now let me start with this slide. This was just recently published in Nature. What are the 7 technologies to watch in 2026? And you see it's xenotransplantation, so that means humans will be implemented the liver of a pig, for example. Can you make it happen actually without any negative reactions? The answer is we are going there, we are getting there, and so on. You have the usual suspects like quantum computing. Very interesting AI-powered meteorology, I come to that later. Will AI-based climate and weather models be much, much better than the conventional approach? And some people like Demis Hassabis, to whom I will refer later, say yes, it will be like this, and so on. I'm here not only as a member of the Academy of Athens, the German Leopoldina, and a few others, but I have also been asked by the president of the Pontifical Academy of Sciences, Joachim von Braun, to speak on behalf of the Pontifical Academy. And now it's a very interesting thing. You know, the Keynote idea is in a way building a meeting place for all academies of the world. And there is an academy which in a way is also trying to do that. But it's not based on Greek antiquity, 2,500 years ago, but on the Italian Renaissance sort of take on Greek antiquity, that is the Pontifical Academy. And I show you now a picture of one of our assemblies, and this was the General Assembly in 2016. And on the right-hand side, you may see Stephen Hawking, for example. So one of the most famous scientists of our time, and he was a member, actually, like many Nobel laureates. So Christos will recognize Mario Molina, for example, and many others here. So, and Pope Francis actually enjoyed to join us for these meetings. And in 2024, we had another General Assembly. Now, look to the person in the first row to the right, that's Demis Hassabis, who is one of the godfathers of artificial intelligence, of course, head of Google DeepMind. And he was awarded the Nobel Prize in chemistry, actually, 2 weeks later. I'll come to that again. And this is the theme of our General Assembly. It is science for sustainability and well-being in the Anthropocene, the term which Paul Crutzen formed, and its opportunities, challenges, and AI, actually. So I show you a few slides from some of the people who were involved there. So here is Demis Hassabis, who became a member at that session, accelerating scientific discovery with AI. And he showed some fascinating examples, in particular also weather forecasting with artificial intelligence. And the question is also, can you do climate predictions based on artificial intelligence? And this is a problem for all who have tried to understand how machine learning works. They are trained by data, of course, the algorithms. But how do you train a system about the future climate where you don't have yet data? So you have to combine conventional computing, as we do it now, based on Lagrangian modeling, with AI data. And marrying these two things may actually be the holy grail of climate prediction in the future. We had a fascinating speech by Anton Zeilinger from Austria, Nobel laureate in physics, on quantum theory and quantum experimentation. But we also had this contribution. That's Eliane Ubarichoro. She's the head of the forestry section of FAO, the World Food Organization based in Rome. And here you see it's AI-driven digital commons that serves people and the planet. So it's about applying artificial intelligence for those people who really need it, who have to make a living on the ground in sub-Saharan Africa, for example. Completely different application. And here, James Liao designed an evolution of new metabolism for carbon fixation in organisms. It's in the end about artificial photosynthesis, which in my view is the biggest invention of all time on Earth. And I'll come to that a little bit later. So what I'm saying is many of the contributions in the Vatican we had in 2024 were in a way applying artificial intelligence to the natural world, but also using the understanding of the natural world to improve our technology. And here's a proposition I would like to share with you when we talk about high tech. Now, you see here in my chart, you have no tech, that is nature. These are the solutions provided by evolution over almost 4 billion years. Time is of the essence in evolution. So nature tried many things which went wrong, were extinct, and when the best and the only survivable ones survived in the end. When you have high tech, and I will populate this chart in a second with all types of items. By the way, cyanobacteria invented photosynthesis. That was 3.5 billion years ago. And you have middle tech. Now, this microphone here, this is not high tech really. It's middle tech. Combustion engine, that's not high tech. I would call it middle tech. What is real high tech? And I'll now populate this chart. So, starting with the bacteria, evolutionary tissues, and so on. In the middle, you have what we call middle tech, combustion technology, microelectronics, composites. And on the right-hand side, you see what really deserves the name of high tech. So, as I mentioned already, quantum computing, nano devices, AI, of course, all types of AI, additive manufacturing, and so on, and synthetic biology. And I think this is one of the most important and also the most critical developments of all. So I spend a little bit of time on that. Oh, something happened. Oh yeah, you still got it. So, sorry, I have to go back here. So, let me see. Just want to go back to the first one I had. Yes. So here we go. Sorry, something always goes wrong with technology. It is like that. So, but demonstrates that I'm a human being. I'm not an avatar or something like that. Then it would all work well. Anyway, so I'm going back to this, and now my main proposition, and through this interruption, you really pay attention now. My main proposition is that the future of technology, the future of the human project on Earth will be combining the two wings here, namely no tech, as we find in nature, and high tech, the way I defined it here. So the two wings will be combined, and this is no tech meets high tech. This is the future of the most disruptive technologies we can think of. Huh? And so in a way, now I steal something which is in the Vatican, in the Sistine Chapel. See? And something goes wrong again, just to increase your attention, of course. Oh yeah, let's see. You have seen, of course, the famous fresco of Michelangelo. And that's what I call the cyborganic age, but nature, the green hand, so to speak, combines with our high-tech arm. And based on that, I mean, the Nobel Prizes in 2024 were all about high-tech meets no-tech. So, for example, you had John Hopfield, with whom I had some encounters at the Santa Fe Institute for Complex Systems, for example, the famous neural network model and so on. Finally, he was awarded the Physics Nobel Prize. So you see Demis Hassabis, for example, David Baker, John Champa on chemistry, cracking the code of proteins. And finally, you had Ambros and Rufkun on RNA of profound physiological importance. Now I promise to tell you a little bit about synthetic biology here. And this is something that can, as the title of this paper is, can either help the world or actually destroy it. So it comes really in 4 packages, so to speak. So gain-of-function research, bioprinting, synthetic viruses, CRISPR, of course. It has an amazing power, really. And if it is supported by the most advanced versions of artificial intelligence, it can create more or less everything on Earth. We have not really understood what the consequences will be. Not even talking about consciousness here. It's simply, you can create all types of life forms, and it will happen unless we have a discourse and regulations on that. So just a few examples. Another one is a major field now emerging. It will be one of the biggest business cases in the world, humanoid robots. Just think of, you have all the possibilities to have mechanical capacities. You have a central nervous system, which is artificial intelligence, but you also can create through synthetic biology tissues, like human tissues. So the humanoid robot will definitely look like a human being. It can all be done, and there is tremendous research on that. Now let me turn to photosynthesis. Why? Because I think this is the ultimate solution to the climate problem. And you have to bear with me for a few minutes how I make this connection here. So, natural photosynthesis, you know, you have water, you have CO2, and you create, with the help of sunlight, oxygen and carbohydrates. That's the basis for all forms of higher life. This is the basis for human beings, of course, because when we eat something at the gala dinner tonight, for example, we will eat carbohydrates, or things based on carbohydrates, and we will breathe at the same time. And while burning the carbohydrates or the meat, we actually bring back the sunlight that was used to create these substances. So it's sun energy that is taken back. Now you can enhance all this in an artificial way, and there are amazing papers about that, and I don't want to sort of bore you with that, just to show you that it's an emerging field of tremendous impact now, and we could look it up. Another way is just bio-based innovation. So there's a company, Stora Enso, based in Finland and Sweden, who more or less promised to do everything based on natural tissues. So energy, the future of electric cars is powered by trees. But more or less you can even build semiconductors, electrochemical transistors based on the bark of trees and things like that. So it's amazing. In principle, everything that is currently based on mineral materials can be replaced by organic materials. That's very important. It brings me to my main proposition now. I was kindly introduced to someone who has more or less created the field of tipping points and tipping elements in the Earth system. So this map here about the tipping elements in the Earth is a version of a lecture I gave at Oxford University in 2001. This is about the subsystems of the global system, the Earth system, which could be changed in character or even destroyed by global warming. So the idea is if you have 1 degree warming, if you have 2 degrees warming, what essential subsystems of the Earth will be changed? For example, between 1 and 2 degrees, we will lose probably all tropical coral reefs, where 1/3 of the marine productivity is created. 1/3 actually. We will lose them if we go to 2 degrees warming. Around 2.5 degrees, the Greenland ice sheet will start to melt, the West Antarctic ice sheet even before. What about the thermoline circulation in the ocean, the Gulf Stream system? Jury is still out, but there is a 50% probability that it will be shut down during this century already, and so on and so on. That's why the 2 degrees is so important. In a bottom line statement, we should stay in climate below 2 degrees globally, simply to avoid most of the tipping events that are on this map. Some of them will happen, but beyond 2 degrees, many of them will happen. These are the biggest accidents we can imagine in climate change. That's why the 2 degrees is so important. Now, where do we stand right now? So bear with me, this is a little sort of exercise in sort of elementary climate physics. On the horizontal axis, you have the time. So we start in 1900 and we end in 2200. On a vertical axis, you have delta global mean temperature change, so that is global warming referred to pre-industrial temperature. Now, here you have the Paris lines, the Paris Agreement in 2015, where, by the way, the Pontifical Academy played a big role because it was the year when Pope Francis published Laudato Si, the famous encyclical. So we were involved in that. So 1.5 and 2 degrees. Where do we stand now? Well, this is, in a cartoon way, the current development. So you see in 2024, we went above 1.5 degrees already. And what is the future development? Given all the climate agreements, national ones, international ones, already accounted for, well, it will look like this. Now, some of the climate scientists in the audience, Guy Brasseur or Christos or Kostas Enoulakis and so on, may think it may not be as bad as I see here, but my physical intuition tells me this is what would happen under climate policy business as usual. We would go far beyond 2 degrees, and we don't know where it will stop. So what is the alternative to that? You see, holding the 2 degrees line is not an option anymore. We will go beyond 2 degrees in the next 20 to 30 years, cannot be avoided anymore. But the alternative scenario, this will be probably the biggest challenge in industrial history, is to do this. Namely, bending the curve back after a long period of overshoot, climate overshoot. And it will all depend how flat and how short actually this overshoot period will be. And I offer to you an option how to bend the curve back actually. And it comes in two pieces. The first piece is if we decarbonize all our economies by 2040, 50, and that is a tall order already. If we do that, we'll at least keep the curve flat. So we will go beyond 2 degrees, and we may stop it when with complete decarbonization of our industries at 2.5 degrees, and then it will stay at this level for many, many years, maybe even for centuries. But to bring the curve back, we have to extract CO2 from the atmosphere. Tremendous amounts. Every year at least 10 billion tons of CO2, proactively. And there are some geoengineering sort of schemes. I do not believe in any of them, actually. They're much too expensive. You would have to create a global infrastructure to extract maybe 10,000 filters and so on, or you would have to pour gigantic amounts of iron into the seas in order to enhance algae blooms and things like that. All these geoengineering things will not work. But there is an alternative, actually, and it's a natural alternative. So, by the way, we will have to weather the storm. We will actually move for 2 centuries through troubled water. That means through this overshoot hump. I think it can't be avoided. This means adaptation will be extremely important. It might mean that the temperatures in Athens will rise to 48 degrees in summer. It definitely could happen. So, you see? I go directly here. Or maybe, if you bear with me one more minute. Let's see. Here. So I recently visited the Weizmann Institute in Israel, which is one of the most exquisite research sites in the world. And they came up with a paper in Nature recently showing how man-made materials compare in weight with biomaterials. So the green line you see here is the amount of biomass on Earth. So it's about, more than 1,000 billions of tons, actually. But in 2020, the weight of man-made materials outweighed, actually, the bio-based materials. Before the Industrial Revolution, the biomass weight was actually double this, and we have already killed half of it and replaced it by anthropogenic materials. And if you look at this material lasagne here, so most of it is concrete. Concrete is the most prolific and distributed and whatever heavy material on Earth now. You have asphalt and bricks and metals, a little bit of plastic. And now the basic idea is to replace this more than 1,000 billions by organic materials. And the most important application is buildings. So, we published a paper in 2020, Buildings as a Global Carbon Sink, and the idea is very simple. If a tree grows by photosynthesis, it extracts a lot of CO2 from the atmosphere. It's stored in the stem. Now, if you burn the wood, then it goes back to the atmosphere, so it's climate neutral. But if you use it for long-term construction of buildings, so you place a house built from concrete, a house built from timber or bamboo in the southern hemisphere, it means you store for at least 2 or 3 centuries the carbon which was extracted by natural processes, the photosynthesis. So in a way, combining forestry, sustainable forestry, and construction based on organic materials you can create a huge carbon sink on this planet. And we've calculated we can actually extract enough CO2 from the atmosphere this way in order to bring the curve back. But it will take about 2 centuries. And ladies and gentlemen, this is the truth about global warming. It will take 2 centuries to clean up the atmosphere, if we go this way, for example. And there are many papers now showing, for example, here in Science, that you could store more than 16 billion tons of CO2 annually by building materials and so on. And when, of course, we could use the principles of nature for adapting to climate change, we could have all types of architectures inspired by nature, as you can see, and I do it quickly. We had a conference on this. Let me show you this one. So here, we did a conference in the Vatican with Ursula von der Leyen, and the gentleman standing next to the German Ministry for Construction in the first row on the right is Francis Carré, a famous architect from Burkina Faso, and he shared with me these pictures. What you see here is a termite mound in the Sahel, and there's a paper in PNAS showing it's the best ventilated structure on Earth, actually, created by natural evolution. The termites achieved it, but they tried many times, believe me. And Francis Carré now built the Burkina Faso Institute of Technology as a collection of termite mounds, so to speak. And it doesn't need any air conditioning. It just operates by natural ventilation. So it's a fantastic example. It's beautiful, of course, but it is also extremely functional. So let me end with being in Athens, of course, talking about bridging the modern and the ancestral world. And I think it was Alexandra Mitsutaki, who is sitting behind. She talked about AI in the sense of ancestral intelligence. I think that's right. And she invited me. Oh, what happened? So I have to go back. Sorry for that. You see, I'm a okay. This is only to keep you attentive, of course. So, but I'll end now. So there is this famous and amazing idea of having an Alpha Mission meeting on the sacred island of Delos. So those who are of Greek origin, of course, know about it. It is the central island within the Cyclades, and it is, so is the legend where Apollo and Artemis were born. And I had the amazing opportunity to follow up on the famous Delos Symposium by Doxiadis and others, which was about architecture in the 1960s, 1970s. And actually, the most impressive location and venue where I ever had given a speech was here on Delos. You see, this is sunset on the Delos Island, and I had the privilege to give a lecture on artificial intelligence and culture and architecture in the amphitheater of Delos while the sun was setting down. An unforgettable experience, actually. So Kostas Sinolakis was there and a few others here in the room. And in a way, everything comes together here, you know. I talked about nature combining with high tech, and here we should talk about classical antiquity, the insights of the past, the cradle of Western civilization here in Greece, combining it with the most advanced inventions and innovation in the world in order to save the human project on Earth. Thanks for your attention.
Thank you very much, John, for a wonderful presentation. I think now it's time to actually go outside, and we are going to have a group photograph, a historic one, that marks the beginning of the Keynote. Thank you.